Sorry about that, my microphone's in the back. Yes, I unfortunately will not be able to stream later on today, so I gotta do it now. Technically it's after midnight. Well, not technically it's after midnight, it is after midnight, which is technically the same day. So yeah. Hello everyone, welcome to Checkup Day 653. 2 hours after midnight. Hi the deep guy, hi the most. It's 1 AM. Yeah, and that's technically the next day. Unfortunately, I won't be able to stream later today because, you know, walk next week. And so, yeah. So we gotta do a late night stream. A stream that's so late night, it's morning. Hi the lawmaker, hi. This is gonna be an American live stream, isn't it? Because the timing. Let me play some music. Open with VLC media player, there we go. I should really make like a, I don't know, thingamajig. You get what I'm saying. Like a thingamajig for my music. That would play automatically. There we go, and... there we... go. Hi there everyone! Still Europe. It takes more than that to keep the Europeans away, am I right? Anyway, today I thought we could do it, well, we could continue on, I suppose. Which means... oh, I still have the tabs open, that makes sense. So, when it comes to videos, I have been scripting some more with the math video, that's fun. I decided to stream in the middle of my online logic tests. You can go finish it. You got the whole world watching. What am I, Hamilton? That's the lyric, isn't it? The whole world watching. I think the world's getting your eyes on you. I think that was the lyric. What a cool and topical reference, everyone. Hi. Anyhow. Particles, right, that's what I was trying to research. Although, to be fair, the particle video was gonna take a while to finish. Hold on, I'm almost finished setting up the live stream, okay? I start them always unprepared. That's how I like it. There we go. I got so surely there's gonna be a lot of late math done. Good luck on the exams, the most. You're gonna do the most you can. That's the most impressive. Yeah, I'm done. Okay, I won't do it anymore. Anyhow, substructure, nuclear and particle physics. Oh, that's Valet! Oh, that's my favorite one. 1-9, History of Particle Physics. Oh, that is my favorite nuclear physics textbook. Does it go into fundamental forces? Oh, and this one will be our quarks. That's actually could be a perfect textbook for quarks. I do love it. Plan was made on purpose. All my plans are made on purpose. Always. Experiment tools. Wasn't this just about particle accelerators? Yeah. Yeah, I don't care about those. I don't care for those. We have gone through most of this stuff. Like a while back in the stream too. Funny enough. I just wanted to say hi, goodbye, make everyone have a great time, thank you everyone. Bye deep guy, bye, chromodynamics, color. It actually is color. It really is color. It really is color. Because quarks have color. There we go. That's like their unique property. Oh, unique. And flavor. This is gonna be so confusing, I can already tell. It's gonna be fun. It is gonna be fun. I should probably go through it step by step. If I remember correctly, the 4th chapter is where things began getting interesting. But this is still just nuclear. And nuclear is not quite what we're looking for. So for now we can turn it off. And we can Because it will be particle physics, correct? I do believe so. Nuclear and particles. There are only 2 textbooks, by the way. So yeah, that's fun. Thank you so much. I went to their website and learned a lot. I'm going to use it every day. I do use it every day, actually. Would recommend. University physics, classical mechanics, relativity, quantum mechanics, kind of, I suppose. It's not quite quantum mechanics. Modern physics, I guess, but modern physics is terrifying. There are 8 quantum mechanics. Okay, what's chapter 3 like? Is it theory or is it? No, it's not what we're looking for at all, unfortunately. We might need to. Oh, that's annoying. We might need to. We might not be able to depend on LibreText for this one. Because LibreText might genuinely not have the knowledge we need. Unless modern physics will have spiral modern physics. Oh wait, isn't that the one? Oh no. Oh, that is the one. Nuclear physics. How much nuclear? Alpha decay, nuclear physics. Okay, so this is nuclear. Would you happen to have? You have the photon, so that's good at least. Also general relativity, special relativity. Where's the website? It's LibreText. So let me move my day out of the way again. LibreText. Right here. I should be in bed by now. Also, I think the better reminder. Like this info algorithm. Alright, demos. Bye. Good night. And thank you, too. Would be particle physics, correct? Actually, Google Scholar. I don't use Google Scholar nearly enough. I'm curious. Strong interaction. Articles, yes. Theory of strong... Annals of 1960... I guess they're all gonna be pretty old. 2000, that's good. 2003. 1997? But what are they? What are these? No, these are papers, aren't they? Yeah, I guess Google Scholar makes sense. I don't know. I need to find the source. Firefox debunker. Yeah, I'm a DuckDuckGo debunker. Doesn't quite have that same ring to it, does it? One day, some days no sooner one day, make it just the combination of relativity. It's next day! Oh, you can't see the time because I have my avatar over it, but it's 2 AM! That's the next day. Atomic? Jeez. I won't be able to stream later in the day. That's because I have work. And I couldn't just wait like 10 AM or something, because then all of y'all Americans would go to sleep, and that would have been a really short live stream. So, listen, it was either now or never. Or go broke. That's always an option in there. We need to find the source. This genuinely might be a lot more difficult than I expected. Let's go for Wikipedia, because Wikipedia has good sources. Maybe Wikipedia would have something fun. Yup. Further reading, would love some. The strong intro. Oh, 2001, is that the whole paper? Oh my goodness. That's so nice. It's like 8 pages long. That's phenomenal. Oh, I love it so much. Okay, that's tempting. Introduction to elementary particles. That also sounds like something I would be interested in. Hold on, can I... Okay, that's not looking for though. Oh, but this is... Oh, I see. Oh, that makes sense. Not open, so that makes sense. I don't want to pirate this. That's... I don't... Google Books. Is it gonna be... Festival Capture? I'm not interested. Not that committed. Collapse and rejection course to modern pack. Okay. That's an archive that... Oh, yes. 400 pages. That seems like quite a read, doesn't it? Some pages are omitted. Indeed, they are. Like, in between page 10 and 424. Those pages really seem to be omitted. That's... Some pages are omitted, I suppose. Is it digitized? I don't mean to be that guy, but there seems to be a book missing in your book. I mean, pirating can be for the great good. Well, I mean, yeah, but it is legal. The Last Sorceress, path from alchemy to periodic table. That sounds awesome. I mean, this is already something. Strong interaction is the one we're looking for the most, because quarks are the most confusing. I guess bosons too. Oh no, quarks. Yeah, and I guess bosons will also be annoying. Do you sleep? No, I do not. Why? Why would I? There's work to be done. Once I'm finished with my walk, I will sleep. Alright, so this is something. This is nothing. This is... Open library. One to read. I'd consider it 5. Legality is optional. Unfortunately, it isn't, because, you know, prison or fines, whichever. Actually, fines might be worse in my case. Prison is at least an excuse. I can be like, oh no, I can't stream, I'm in prison. Like, that's a valid excuse, I feel like. I could also escape. That's a whole other thing. Alright, so... I guess this would be enough, because that's a strong interaction after all. Let's go elementary particles. Let's add it to our source side. And right here for elementary particles, what we want, what I feel the weakest on is... Actually, a good question. I feel the weakest on everything, I should research everything. The version quantum physics video. Oh, I'm glad you liked it! Okay, external links, further reading, yes. Feynman, I heard that guy was pretty clever. Drag Memorial lectures, okay. Physics for everyone, that's not how you spell everyone. The elegant universe, superstring sin dimension, the quest for ultimate theory, we're not really interested in that yet. Key for quantum particle physics. No. Facts, mysteries, and elementary particle physics. A very short introduction. Would you happen to have that like, for free? Please have that for free. That would be just so grand if you could just... Publishing hours of University of Oxford. Would you happen to have like an online copy I could read? Well, that would be really convenient. Nothing like some try and make it, I guess. Exactly. Also, is there a book in this book? That certainly seems like a book. That's a... Oh my goodness. That's a book. Oh. Hell yeah. That's a book and a half. Oh goodness gracious me. Yes. That's a win. Just use some of the cancer funds. I don't quite have the access to that yet. That's a book. Greg, just like minutes ago, there was a book with no book in it, so you know. Okay, that's something. That would be good for background of particle physics, although we do want to go more in depth. We basically, ideally, here's the thing, ideally I would like to talk about all of them, although that won't be easy. Really will not be easy. Because there's a lot, you see. Do you think Wikipedia should remain free, or is it being free to all against capitalism? What? Hold on. Do you think Wikipedia should remain free, or is it being free to all against capitalism? I don't get the other question, Gemma, to be honest, but yes, I do believe Wikipedia should remain free. Mainly because I use it. I don't want to pay for it. That's expensive. If I had to pay for Wikipedia, I don't think this channel would be where it is. Okay, up quark, champ quark, top quark. Well, obviously we're gonna have up and down first. top and bottom, then charm, then actually charm could be right here. Up, down, charm, top, bottom, strange, electron, obviously, we have to have electron. Tau, neutrino, muon, I have no idea about these. I just simply do not know. Free open source, the best source, it really is. Some pages were omitted, some books were omitted. It really was, there wasn't a book in that book. Electron, neutrino, I'm not really great with leptons. I'm really awful. Bosons, that's easier. With bosons, obviously, we're gonna start with photon. That's a da. W and Z will be next, and then gluon because quarks. Although we could actually talk about the gluon. That's tricky because the gluon should also be Lyon next to the quarks. And then Higgs boson, obviously, last because it's cutting edge. It really is. When was it confirmed? Discovered 2013. Like. Oh my goodness. 2011, 2013. Discovered. Particle. It's insane. There were some people, or there will be some people statistically, who would have seen this video. Actually, no, wait, that goes counter to the point I'm trying to make. Everyone seeing this video will probably be older than this particle. Is there a Make It wiki page? Unfortunately, there isn't. I wish there were, but there isn't. Make It. Hold on. Make It County. There's no Make It. There isn't even a disambiguation page. I'm not upset. I'm just sad. Would there happen to be like a book about quarks or like a short thing about quarks for the reading? European Physical Journal? Oh, hell yeah! So the discovery of quark and gluon. That's what I meant. Quarks and gluons should be probably together. Quarks? What is this? I am not a robot. Bicycles? Those look like bicycles. Ah, I was joking that I am a robot. Why is that cake? I can't content steal, I'm sorry. Shall we gonna get to walk? Yeah, agree. That's what I'm trying to do. Oh, unless you mean Wikipedia. Oh, please do. I would love to. Oh my goodness, the flex. Oh, you know how much I would be flexing if I had a Wikipedia page? I would like, you know, go to restaurants and be like, hey, you know who I am? And they'll be like, no, I don't. Then I will show my Wikipedia page and they'll be like, cool, I still have no idea who you are. And then I'll be like, oh, I'm sorry, and then I would just start and then I would just pay and then I would just leave. Oh, it would have been so great. Wikipedia had to go no matter what it says. I agree, Wikipedia is the best. I mean, as a source, you still shouldn't use it. Not really because it's untrustworthy, only because you're not going to get much in-depth information of Wikipedia. However, it is still great for just... as Wikipedia, it still works. And because all the links are there, you can just... Physics non-practice lecture. Tempting. Whoa, that's aggressive music. That's much better. You are popular enough to be on Wikipedia. Am I really? There is no way. I don't think so. I don't think I'm popular enough to be on Wikipedia. If I am, then I'll be honest, I'm upset. Is the Star Wars in Poland? No, we haven't invented Star Wars yet. We'll just classify you under the Polish page. The cake is not real. You mean to tell me that the cake is not the truth? Like a lie? What is that reference? Listen, if I had a Wikipedia page, I would link it under each video in sources. I really would. Someone please explain to me what the W and Z bosons do. how in-depth of an explanation would you like? Because I can do a simple explanation. They are carrier particles of the weak force, weak interaction. That's it. That's the surface level one. If you like in-depth, then it's really confusing because behind gravitons, they are the absolutely worst carrier particles, or the most confusing. So I would say that photons are the most carrier of the carrier particles, so it's really obvious to see how they work. Gluons also, mainly because they're so quantum, but bosons, W and Z bosons are just, they are used for the weak interaction, but the explanation of how is incredibly confusing. I know that didn't help or clear anything up, but that's my knowledge right there. You hate all carrier particles you make. I love the photon. I love the photon, I love the gluon. I don't hate the boson. Boson is just confusing. I don't like the graviton. Yes, I do not like the graviton. Because it can't even be renormalized. How cringe. Reaction to elementary particles. Can I invest elementary? Oh. Will there be a book in my book? Or will there not be a book in my book? Because I'm gonna be honest, I would rather have a book in my book. May I have a book in my book? I know if graviton is even real. It's theoretical. It's so... no, it's not real. It cannot be real. There seems to be a problem, unless I'm off. Oh, you won't even let me refresh. That's curious. Reload. There we go. What's the problem? The 0 gigabytes. I don't think you need gigabytes in there. What happens if instead of this, we just this whole thing to remove the reefer? Nope, didn't help. It did help. I'm a genius. My goodness, I'm so clever. Is there a book in my book? Oh no. There is no book in my book. Damn it, it's the second time. Let my book have... I mean, Greg, you're joshing around, but there is no book in my book. Look at this. There is no book in my book. It's just the first page and then the last page. That's it. It's the second time this happened. I'm assuming they're being removed for copyright reasons, which, like, fucking... why we archive stuff? Doesn't matter. The point is... sociological history of particle physics. It's wild. Elementary particles seems like it would have been useful, certainly. Wait, login and borrow? Oh... I'm an idiot. I might be an idiot. May I... oh, may I now? Please do. I'm creating an account just for the... oh my goodness, yes, please. My books have walked. Make it first time on stream. How are you doing? Hi, Dry. I'm doing well. I'm doing well. Thank you very much. Just doing some light researching, you know. Two-page book won't be so bad an idea considering how short people's attention span are these days. Maybe the book wasn't from us. Yeah, maybe the book was just the friends we made along the way. It's still creating an account for me, by the way. Well, I guess we'll get back to it. So that could be... that's actually elementary particles. That's not only quarks. That could be actually perfect. Okay, so we already have one book that's particle physics, basically. Elementary particles. And that's Dirac Memorial Lecture. So that should be pretty accurate, I would say. Also, that Feynman guy, ahead, he's pretty good at this whole physics thing. Light history, how 2 books. I think that was just me being an idiot, to be honest. Did my account get created, or am I accountless? Sign up for free. Okay, it's still registering, so I guess I'll just let it cook in the meantime. And right here we will just actually no, first we need to research this, at least in a bit. Welcome class into another reading of Fantasy of the Century. I agree. Okay, we're gonna be skipping over a lot of things which aren't quite as relevant, simply because I'm working with limited time here, okay? I'm on a strict schedule, we kinda need to... This is like... I kinda need to speed up. So, that was lecture somewhat incomplete because I really want to talk about two subjects. First, why there are antiparticles, which I absolutely love that topic, because I already have one library textbook which explains that it's great. And second, the connection between spin and statistics. Yes, okay. When I was a young man, the rock was my hero. Doing physics was... guess at the form of an equation. Equation we now call Dirac equation, and try and interpret it afterwards. Be here. Okay, cool. There we go. Reason for antiparticles. And the interesting angular momentum that the equation demanded was the key, and spin was fundamental consequence of relativistic quantum mechanics. However, the passive negative energies that the equation presents. Okay, so this is the E squared equals, because that's, I love that equation. So this is still the introduction, correct? Last, was the chemistry bit. I was only there for the last half of the premiere. You mean the... Oh, the recent chemistry? That was a really good one. Okay. And yeah, you can do it for any spin, as Polymerics proved, and therefore I want to start the other way about. Try to explain why there must be antiparticles if you try to put quantum mechanics to relativity. Walking along these lines will permit us to explain another grand mysteries of the world, namely the Pauli exclusion principle. The Pauli exclusion principle says that if you take the wave function for a pair of spin half particles, then interchange of the two particles, then to get the new wave function from the old one, from the old you must put in a minus sign. Chemistry, I'm not saying I'm done in physics. Have you seen the chemistry video? Oh, so you've only been for the second half of it? My goodness. And I wonder why this video isn't performing as I expected. That's because Greg didn't watch the whole video. What's the stream about? Oh, it's just researching for a video. I plan on making a video about elementary particles, but unfortunately I don't know enough about elementary particles to make it yet, so obviously we have to research the topic before scripting a video. Half particles, okay. Christian itself, with the existence of antiparticles, the pair production of particle and possible, for example, electrons, positrons. Machine now is, if we produce an electron and a positron, why does the new electron has just been made have to be anti-symmetric with respect to the electrons which were already around? That's so in depth, actually. Why can't it get into the same state as what? Okay. So, a long time ago, the wages in the spirit. Okay. Going to go further back to Maxwell's gear wheels, cheese, and try this. We're looking at nothing. It's simply exposition. I love it when people just make this whole thing. I guess I am adding nothing too. I'm just. I guess I should actually put that quote in my video. I am adding nothing to what is already known. What follows is simply exposition. Pretty accurate. Page red lines under every vid. I've watched all my videos. They're amazing. Here he goes to how things go. Why there must be antiparticles. Okay. First, relativity and antiparticles. In ordinary non-relativistic quantum mechanics, if you have a disturbing potential U acting on a particle which is initially in a state phi null, then the state will be different after disturbance. Makes sense. Up to a phase factor taking h bar equals 1, the amplitude to end up in a state g, my god, that's a lot of characters, is given by projection of g onto u phenol. In fact, we have oh, fun equation with brackets. That's good. Is equal to negative I. What is this equation? That's the first equation of the book. Okay, the expression, that's brackets. That's kind of understandable. At least, no, don't skip over yet. Is Dirac's elegant bra and kid notation for the amplitudes. Although I will not use it much here. No, please do use brackets. That's the simple one. I suppose that formula is true when we go in relative quantum mechanics. Okay, so we have u phi. That's a complex conjugate, isn't it? Great. So we have u phenol. Phenol is the initial state. U is the potential acting on it. So we take the potential, we multiply it by the initial state. As the complex conjugate is there also for some reason. To end up in a state G. Okay. What is amp? What are we calculating there? That's what I don't understand. I'm already stuck. My goodness, that page 20, stuck. There are two disturbances on time t1 and another later time t2, and we would like to know what the amplitude is. Okay, it's amplitude, makes sense. Is for the second disturbance to restore the particle to its original state, phi 0. We call this first disturbance u1 at time t1 and the second u2 at time t2. So far, makes sense. We will need to express the successive operations of the disturbance u1 evolution from time 1 to time 2 and the disturbance of u2 okay. This we will do using perturbation theory. Of course, the simplest thing that could happen is that we go straight from phenol to phenol. Amplitude 1. Okay, makes sense so far. Maybe this book was too powerful, so they made it bookless to conceal its power. I mean, it isn't what I would call easy, exactly, or simple. Leading on the perturbation expansion, this next to leading on the disturbance, you opening a state of phi instead. Okay. Hi there, Harpy. Welcome. You're an edgy 11-year-old. That means you're actually younger than... That means you're actually younger than the Higgs boson. No, up to this, we see that. Okay. I won't sit here and pretend as if I understand. E equals square root of p squared plus m squared. Kind of makes sense, I suppose. Wait, no it doesn't. I'm lying. Particle of mass m. These E factors are arranged just to make particle relativistic properties more apparent. Invariant momentum density. The process can be written pictorially in figure 1, which is this. Festive. Do elementary particles have a half-life? Quarks, I suppose? There is the weak force acting on quarks. I suppose you can consider that a half-life. So basically quarks can switch around. You will understand the simple examples, because if you do, you will understand the generalities at once. Okay, let's assume I won't. What then? What happens if I don't understand the simple examples? Because, to be honest, I know this. Okay, that's something I know. Fourier can be good positive frequency only. Okay, yeah. Fourier, good. Can we stick with it? Can we stick with Fourier? Okay, now here's the surprise. If we evaluate the amplitude for any ax and bx, we could even arrange for ax and bx depending on p, festive, we find that it cannot be 0 when x is outside the light zone. The account... Okay, the account is still... I'm still getting registered. Oh no. Do I need to confirm it like an email or something? Maybe that's what I need to... Maybe I just need to confirm it in an email. Maybe they send me like an email to confirm something. No? Just receipts from Google. Okay. Good. Understand the complex examples. I am struggling with the basics. This is way too advanced for me. Like, I don't understand the integral d third x. I don't understand why it's there. Why third? That's a pretty big problem. Just because dimensions. It might be. Already other original thing have a half-life, which has since the half of the time of one atom takes decay into an atom's energy. Yes, that's half-life. So elementary particles don't really have half-life, simply because they don't really decay in that substance, but they can change, so you could consider that a half-life. A cup of coffee might help. Happy, you're so right. Give me a second. It doesn't. It does not. Besides, this I just realized this is not what I'm looking for, actually. I mean, it's fun. This is hell itself masquerading as simple things. Maybe this. Okay, no, this is doomed. This is doomed to fail. Why can't I just get my login and borrow? I can't log in and borrow because you won't accept me as a user. Sign in as make it. Yes, sign in as make it. Fund an existing account. If you link it, then if I have an account, why do I? I swear, I'm. Thank you. Borrow. Why do I need to borrow it? If you know what, I am. Whatever. I don't care. I don't care. Why would I need to if it's free, why? I am fine. I understand perfectly. It's obviously you need to borrow a book that's available for free online, and then when you why it renews automatically? Why would I ever need to you know what? I won't ask any more questions. It's obvious, makes sense. Cool. Alrighty then. What do we have here then? I suppose 2-page view, I prefer it for some reason. Actually no, 1-page view is bigger. I like it more. And full screen. There. Okay. Introduction, particle accelerators and beams, particle detectors, pions and muons, that's where you start. Supposed to make sense. Mesons though. Well, I'm not gonna question it. I ain't gonna question it. Wait, how far do we want to go? Because I don't really care about accelerators, to be honest. If we want to go on page 40. We can email it now. You do realize you can also check my email on YouTube. There's like a button to show the email. Not a secret. Internet Archive doesn't suck. Internet Archive would never suck. It's still free information, and I'm gonna take free information whenever I can. Astronomer neutrons and prions once thought to be elementary are in fact made from more basic constituents, the quarks. Thus the force between, say, two neutrons is basically the resultant of the force between two groups, each of 3 quarks. In this respect, it is approximately analogous to van der Waals force between 2 molecules. I actually never thought of it that way, but that is actually an extremely good analogy. Each of which consists of several atoms. As in the case for the atomic and molecular problem, so for particles it is for many instances. However, very useful to treat the forces between particles as nucleons rather than the forces between their constituted quarks. Although many of the ideas concerning particle interactions were developed before quarks were identified as the constituent of nucleus mesons, these ideas are in general not invalidated by the discovery of the quark structure and are indeed the subject of perhaps best understood by means of semi-historical approach. Cool. I don't love the semi-historical approach, but let's go for it. You can contact Make It relentlessly. Finally, we can contact Make It! Bye, Slade. Bye, Greg. Bye, have a good one. Everyone's either suing it or hacking it right now. Why would you sue it or hack it? Archive. Poor archive. Free information online. Hi, the Tefta! Hi, how you doing? How are things going? Make a video coming soon, the team, but the situation is crazy. I am really going too deep into physics though. I'm starting to be... I'm becoming biased towards physics. Physics is already the field I know the most about, because you just pop in and see what you're up to. Oh, just, you know, light reading. Just having a light read about mesons. How are things going? Answer you busy, that's why I don't bug you often. But it's always such a nice time when you join them. Reading bookless books. Well, that was kind of on me. I didn't realize I had to get the book, which I don't know why that button is there. I'll be honest, I don't understand. This is not technology, this is the opposite of technology. The prediction of the mesons by Kawa in 1935 and the subsequent discovery of cosmic radiation present one of the most striking examples of the interaction of theory and experiment in modern physics. Finished prototype, go to read on the PC, bracelet plus labor. Hell yeah! Oh hell yeah! I myself am starting to turn to full-time YouTube after. It's kind of fun. So that's why I'm so sorry I haven't been interacting with your things, but I'm trying to it's not nice though, that's the problem, because last week I had no freelance work to do simply because I didn't try to get some, and I was a mistake. That was a mistake. My videos are doing really well, but they're not doing well enough. They really aren't doing well enough. Oh no. Well managed. Question, why is the term half-life used anyway? One edge full atomic lifespan. Lawmaker, don't question anything in chemistry or nuclear physics because it doesn't make sense. It never makes sense. It would never make sense. Things there just exist because people letting them make it stream in my dreams now. Good morning. Hi, this is them. Yeah, this is the dream stream. Introduce some high sub YouTubers. Oh, do spill. I'm curious. Oh, I'm jealous. I'm jealous now, honestly. Because it's a reference to the video game Half-Life. Yes, exactly. Actually, the first person to invent molecules, their name was John Molecule, named after himself, actually was such a big fan of the game Half-Life that they've named the Half-Life after after the game. That's a true story. Yeah, it really happened. Oh, science. Those were the good old days. Can you believe that Half-Life 2 is older than the Higgs boson? Invent molecule. Yeah, John Molecule, inventor of the molecules. He invented yeah, that's a true story. That's a true story. It really happened. I was there. I would know. No. John Molecules invented molecules. He didn't discover them. His wife, Suzanne Reaction, invented reactions too. Those were wild times. The atom table is invented by a carpenter. Molecule, name after molecules. Yeah, exactly. It was wild. I do gotta say that's positive on the funniest things. I keep getting distracted. I have a few connections to open source. There are some building YouTubers. I'm getting jealous. Robert Jumping invented jumping. Oh, Robert, that was a what a chap, truly. Halftime still full lifespan. As I mentioned, Lawmaker, you can't question it. You really can't question it because it doesn't make sense. You might as well ask why Avogadro's constant is equal to that sort of garbage number instead of 10 to the 24th. There is no justification. There is no answer. I'm attending these upcoming episodes. Oh, Mellow Labs might be there actually. Mellow Labs goes on a lot of these conventions. So I might see you on Mellow Labs' stream actually. Can't go myself, unfortunately. Money. Open source. Oh wait, isn't that the big one? Isn't that the big convention? Open source. I just realized why that name clicked with me so much. Isn't that the big one where even Nilered got invented? Jeez, I really need a break. Where even Nilered got invited. The I word I was looking for. Too much physics recently. That's exciting. 2025. Oh, it's already 2025 around the corner. Nilered got invented by open source indeed. I am tired. Okay. Why is Avogadro's number not equal to 10 to 24? Because chemists just hate fun and hate logic. I've opened master booth, hopefully. Oh, that's actually so cool. That is so awesome. It always sucks because no matter what I do, whenever I just get back in touch with you, you always manage to do something cooler. That's not fair. Okay, one more sip. I can make it. I have a business meeting in the morning, and so I can't really afford to... what's the name of it all? I can't afford to be late. Yes, I'm forgetting words like these now. I can't afford to be late, and so unfortunately, instead of sleep, I have to choose coffee at this point. Which is fun. So you'll all have to excuse my, you know. What business? It's not business. It's a business meeting, as in, you know, meeting. It's not a business meeting in that sense. It's like a meeting for a job thing. I just call it a business meeting because I don't know any other descriptions. Anywho, particle physics. We can understand Newcover's argument in a quantitative way as follows. It had become well established that electromagnetic forces could be well understood in terms of a field of which the quanta were photons. Yes, made a whole video about this. In this theory of quantum electrodynamics, the forces between two charged particles are attributed to the exchange of photons between them, carrier particles. Hence the name, they carry the interaction. Thus, for instance, the center of mass system, see Appendix A2, The Coulomb scattering of 2 electrons is described by a diagram like figure 2.1. This one. Oh, Feynman. Absolutely love it. Lovely guy. Where energy and momentum have been exchanged by the exchange of a photon. This diagram is similar to so-called Feynman diagram. Oh no, never mind, I was talking about the wrong one apparently. I might just forgot here. Right, Status Pretzels, bye. Have a good one. Of course, to use quite frequently. The more usual convention is to represent the process simply in the figure 2.1b. Let's first notice the broad quantitative features of the nuclear electromagnetic forces. Okay. Evidence is available from static nuclear properties that from scattering experiments. Our purpose here is not to treat these subjects in detail, but rather discuss briefly those aspects which are relevant to the size of the nucleus and strength of the nuclear forces. Okay, I'm all for it. I'm all for just talking about it briefly, to be honest. It is immediately clear that the nuclear forces are attractive and sufficiently strong to overcome the Coulomb propulsion, which is why atoms exist, which I think is awesome, as I already mentioned in the video too, that, you know, the spillover force from the strong interaction is more powerful than the entire electromagnetic interaction, but that's a whole separate thing. It's also clear since nuclear radius R obeys the relation, this, where R is the constant and A is the mass number. Makes sense. There is some sort of repulsive core which prevents the collapse of all the nucleons to the range of the nuclear force. We note that the binding energy of nucleons in nuclei is about 8 million electron volts throughout the greater part. This is not quite what I was looking for, though, I just realized. Because this is weak interaction and strong interaction and electromagnetism, so not quite. Are you a believer in the electromagnetic theory? No, I don't think electricity and magnetism exist. I'm a skeptic. I don't think they exist. I've never seen any evidence of the so-called electromagnetic interaction, you see. They say that you can't see it because photons themselves are the electromagnetic interaction, but I think that's just a convenient lie, you know. Oh no, you can't see the electricity because light is electricity. Yeah, right. Honestly, ridiculous. Should come up with a better excuse. Psi function, of course, our beloved. The exchange may be channel spin, but from any combination of these properties. Just in that the internuclear force was due to some kind of exchange was first thought would make sense. So this is just quantum mechanics, basic quantum mechanics. Let's consider scattering neutrons problems in this case. Quantum force absent. The energy, say 100 mega electron volts, which also is insanely high energy. The quantum scales are wild considering how much energy they have. It's truly insane. In the case, actually, I know this might be a bit of an ADHD tangent, but energy of the strong interaction. What is it exactly? It was in electron volts, not never electron volt. Okay, maybe. Quark, I suppose. Quarks and then electron volts. Much case. Ah, there we go. For example, a proton has a mass of approximately mass measured in electron volts. That's just phenomenal. If you don't measure your mass in mega electron volts per speed of light squared, what are you doing? I mean, it makes sense because, well, Speed of light squared, I suppose that comes in because it's a rest energy in relativity, and mega electron volts, that's just energy. So if you take the energy, if you remove from it 2 times time and, well, squared times squared distance, you do get mass back, but it's an absolutely wild way to get mass. A proton has mass of approximately 938 mega electron volts per speed of light squared, of which the rest mass of its 3 valence quarks only contributes to about 9 mega electron volts per speed of light squared. Great. Much of the remainder can be attributed to the field energy of the gluons. Right. Okay, so we have... Right here we can get the energy actually out of it. It's going to be an approximation, but still, because the divide by speed of light squared, if we pop that off, most of it should be just the... Oh, but that's going to be nuclear, isn't it? Do we not have an electron volts? EV. Much case. There we go. No, it's mass. Okay, in this case, you're just measuring mass in mega electron volts? Come on. That's... Hold on. Why you measure... I don't even... Also, this is... I don't even understand what... These are quantum numbers must be assigned the quotes different... Oh, okay, I see. Quantum numbers. Why do we need so many different quantum numbers? Why couldn't you just have one? Doesn't matter. I won't get into it. Baryon number, I feel like you don't need that there. Charge. I'll be honest, I had no idea... What? How come I've never realized that quarks have charge? I think you're too tired to register new information. No, I'm not. I'm registering quite a lot. That makes so much... That's why protons have 2 up quarks. Okay. Now I remember that protons... Okay, protons have 2 up quarks. That makes a lot of sense. Although we still need a better source than this, because those elementary particles talks about a lot of different things, and it's gonna take me ages to get to information I would need. Process is going to be much for absent problems if we say this. Mm-hmm. And there's also node exchange forces. Whenever the forces between the 3 possible pairings of nucleons, NP and NP, are the same, apart from the Coulomb's force between protons. Information at this point can be obtained from a combustion mass of energy, so-called mirror nuclei. I don't think that's all we're looking for, because that's a bit too big. Indeed, that's very much not quite what we're looking for. This is like a semi-historic. Yeah, this is a semi-historic account. So it's instead of going in a physical way, as in, I know, from the smallest up or from the biggest down or from forces to particles. It's going historically, which also coincidentally will be from higher up down. So that's pretty cool. Pioneers, no. Maybe Pine's such a weird one to go in with. I'm not gonna lie, I was looking kind of for quarks more than anything else. Let's go back to the starting page. Let's see the... Okay, so we have these interactions, right? Why is Quark the Quark model chapter 10? Oh no. Oh no, 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 no. That's not good. That seems pretty bad, actually. That seems pretty terrifying. Mm-hmm. This has a lot of information that would be extremely useful to me, but it also has a lot of information that I won't use. This book would be great if we were to make like a, I don't know, 30-hour long live stream, at least 10 or 3 10-hour long live streams in a row, because then you could really get into it, but unfortunately a bit too general, which is not something I thought I would complain about, actually. Fed reading. Registration required. Instant... Oh, come on. Sucks. Wait, standard model. Yeah, that's what we're looking for, isn't it? Because I might have a video. Oh, I can't just steal another person's video. Oh, archive.org, my beloved. Internet Archive. Mwah. Appreciate a good starting point. I already know what elementary particles are all about. I know the basic idea. The basic idea being what Kurzgesagt would give me. The problem is, I need in depth. I'll be honest, I'm just sad that there's nothing on LibreText. Because LibreText is always my go-to, so to not have anything on LibreText is terrifying. Freaking chemists holding all the good books. The standard model, chapter 11. That's never good. Never good when it's really laid into it. There's an optics. Oh, it's an OpenStax one though. That's good. Okay, because physics, nuclear, particle physics, cosmology. Isn't this just like the one we've seen before? That ended with chromodynamics. Remember why the good Lord gave you eyes to plagiarize, only of course remember to call it research. I can just borrow it now. There, I've borrowed the book for free. Why is that button there? I don't know. To confuse me, apparently. What do we have in here? There we go. Introduction, true movers and shakers for nature, Great Awakening, the modern physics revolution, merge of relativity and quantum theory, relativistic quantum field theory. I have no idea what these names mean. Modern physics revolution. Is that a history of... Okay, forces of nature, that definitely will be 4 fundamental interactions. Except in this case, I'm assuming it will be 4 plus electroweak. Modern physics revolution... I have no idea what that's about. Merge of relativity quantum theory, that's self-explanatory. Fundamental building blocks, that could be patterns in nature though. What's this? Oh yeah, I have to go to myself, I forgot. 93. Ask if you corner a particle physicist and ask her to explain the standard model of particle physics to you in 30 minutes or less, about the best she can do is describe the so-called building blocks of matter. The relatively small set of fundamental constituents that, when coupled together in various combinations, fully account for the content of the material universe. Oh, that sounds like exactly what I'm looking for. Yes. Haha. Yeah. Any thoughts about the origins of life research? Not really, except for that one fun PhD project in which you're literally the Frankenstein. Except not the doctor, I suppose. Because the PhD project, you get it, pun intended. Discovery was representative content somewhat akin to describing a musical work by citing its progression of chords. Whereas a fair picture of the mechanical structure of the work doesn't get the essence of its beauty. Nevertheless, one does need to delineate the progression of constants in the work, and likewise we need to introduce the list of fundamental invisible particles to appreciate the fully conceptual nature of which. Okay, so I feel like, first of all, this made me just realize something. So I can put it on the screen, not spoil anything, but it made me realize that what I should actually do is strong interaction, then quarks. Then for leptons, actually, I have no idea what goes here. And then bosons should be introduced actually after quarks. I feel like bosons part 1. Then after leptons we'll have bosons part 2. Connection to fundamental as a nice loop-to-loop. And then the Higgs boson as the last. Genuine egg got fertilized. I mean, you're joshing around, but research on how life began basically boils down to chicken or the egg. Basically what it boils down to. That's because you have proteins, and then you also... was it DNA? I don't think it was DNA. But basically you had proteins to create... I don't think it was DNA. Let's just say DNA for now, simply because I can't remember it exactly what was it. So, you need proteins to create DNA, and then you need DNA to create proteins. The heck, I'm searching nothing. What the heck, I'm searching nothing. So, that's the wrong one, this one. 3 quarks from Master Mark, the 8-fold way. The rapid development of particle physics, experimental technique, and particular development of particles created in a bubble chamber, which provided a visible record of the powers of individual subatomic particles emanating from high energy collision, led to a great expansion of the list of elementary particles in the 1950s and early 1960s. At first, particle physics was euphoric.
Physicists were euphoric about the rapid pace of discovery, but as the list grew longer and longer with no apparent landing order or structure, the euphoria gradually gave way to frustration in the sense that this burgeoning array of new particles carried with them some new important message about the structure of matter that we were simply unable to comprehend. The American physicist Will Stubbs, in his acceptance speech for the 1955 Nobel Prize for the discovery of subtleties of the spectrum of light emitted from a hydrogen atom that could only be explained via the application of relativistic quantum field theory, and thus provided one of that theory's earliest confirmations, put it this way. The find of the new elementary particle used to be rewarded by a Nobel Prize, but such a discovery now ought to be punishable by a $10,000 fine. That's a pretty great quote, I've got to say. In retrospect, the particles that those physicists discovered were no elementary, but instead a combination of a much smaller number of truly, at least as far as we know, individual particles known as quarks. The problem is that the aptly named strong force binds these quarks together so tightly inside these prior-day elementary particles that it is impossible to pry an individual quark away and observe it in isolation. The direct experimental evidence for the presence of quarks, which emerges only when the energy of the probe being used to look at them is large, subtle. It required a good deal of head-scratching in the late 1960s to recognize that such probes were recoiling off something small and hard inside the designed designated elementary particles of the 1950s. How did we discover quarks, actually? Now I'm thinking about this, you know, how did we discover quark? Wait, what? That's a good question. In the early 1960s, a physicist at the California Institute of Technology by the name of Murray Gell-Mann interpreted the particles observed in the emerging array of elementary particles as being due to symmetry possessed by a smaller set of internal degrees of freedom, quarks, without ever splitting those particles apart energy particle beam. This insight established a well-defined structure within the array of elementary particles, an achievement for which Gell-Mann was won in 1969 Nobel Prize in Physics. Okay. Cool. Smashing two atoms together very, very quickly. Yeah, but if you smash two atoms together, still, you're not going to be left with any individual quarks, are you? Because the strong force is still binding them together. How do you break elementary particles that are bound with the strongest force in the universe away? There is nothing stronger than strong force. How do you break them away? I am confused, to be honest. Kind of an obvious thing to ask, too. I don't know why it took me such a long time to ask the question. No, I don't understand. I'll be honest. I guess that's what the chapters about particle accelerators are. Particles with high energy particle beams. So you split them with high energy particle beams using strong force against itself. But that's the problem, though. How? High energy particle beam. If you smash a particle together at high enough energy, it would need to be energy that's high enough for it to break the strong force, correct? Making them hate each other, love triangle. No. They're in a healthy relationship. They have their own bottoms, they have their own tops, okay? Such a dumb joke, my goodness. Give me a $10,000 fine for that joke. Okay, I get why you would get a Nobel Prize for this. That is pretty groundbreaking, or rather, you know, nuclear breaking. The development that said the Apple Railway was a static model of strong nuclear force referred to eightfold way. Quantum electrodynamics is a theory of the electromagnetic interaction that purports to describe everything that electromagnetism has to offer, from high energy, matter, antimatter annihilation, the most basic binding properties of atom. The eightfold way, on the other hand, provides a framework by which the array of fundamental particles previously jumbled, mass of vaguely related particle states can be answered into a basic underlying principle. It does not provide a theory of interaction of these particles with each other. Statically. Candid quantum field theory of the strong interaction. Okay, so that makes sense. Quantum chromodynamics. Okay, so it would make sense that relativity and quantum chromodynamics are the the basis of modern physics, because relativity gives you gravity, quantum relativity gives you electromagnetism, or electroweak to be more exact, and then chromodynamics gives you the strong interaction. So that makes sense that all four of these interactions come from there. Man, Sophus Lie. That's an awful name. Pronounce Lee. Oh, it's Sophus Lee. So Lee groups. Okay. Cool. Hi, the Zoltan. We find out what's in the inside stuff by breaking it open. But has a great documentary about the particle theory in Texas. I'll just have to. I mean, I could just go to the first chapters of the book, I suppose. Okay, connection between physical symmetries, the pattern that observe and the behavior of the natural world. Detailed content of the theories describe behavior. Brings the body of war and Lie groups and end up rediscovering most of the necessary mathematical results on its own. The attraction of beauty is marriage between the abstract pursuit of pure ivory tower mathematicians and the world of theoretical physicists. The connection between abstract mathematics and formal theoretical physics is even stronger. One of the latest practical opportunities was pinned of the 99th Fields Medal, moral equivalent of the Nobel Prize in the world of pure mathematics. Okay, so yeah. Connect to each other by making fake promises. Sudo, are you okay? That's actually a good question. Sudo, you doing good? You doing right? You're right? Whimsically referred to as quarks in reference to a pure line from James Joyce Finnegan's Wake 3 quarks for Master Mark. They called them quarks as a bit! Just like what chemists do with Avogadro's constant. Wow. Cause when assembled various combination would economically account for the myriad of elementary particles having discovered over the course of prior decade. Furthermore, argued Glenman, if the strong force obeys this Lie group symmetry, then the particles formed by binding the quarks together with the glue of the strong force, gluon, have to form the patterns that are characteristic of Lie groups. In language mathematician, the pattern of irreducible representation of Lie group. This is precisely what was observed. The formerly daunting array of elementary particles fell neatly within the patterns of Glenman's eightfold way. One of the emerging particles is now a combination of quarks. However, the rest discovered the precisely predicted properties. Okay, I see. Is that group theory? I'm weak with group theory. Hope it's not. The quarks can be combined together in various ways to produce ordinary nuclear matter, neutrons and protons. These two quarks were given names up and down the alpha way. The up quark has the electric charge of positive 2/3, 2/3 is the charge of proton, while the down has a charge of negative 1/3. If you combine the two, you have a charge of this. Proton, the eightfold way, a proton is the way combination of 2 U's and 1 D. Similarly, neutron is 1 U and 2 D's combination, has no net electric charge. A third quark was required by the eightfold way to allow for the construction of a set of unstable particles have been observed only in cosmic radiation and in bubble chambers that intercept high energy particle beams, particle accelerators, relative to the ordinary nuclear matter. The properties of these particles was rather strange, so this quark was given the name Strange. Pieces are being together properly. The S quark needed to have a charge of negative 1/3, just like the D. The strange quark differentiates itself from the down quark in other ways. In particular, strange quarks are quite a bit heavier than down quarks. Okay, cool. We can already order this bit. So up and down. This is not a... This is a 1. Why isn't it... There we go. Up and down. Strange. I'm assuming that charm will be next, and I'm assuming that bottom and top will be last. That's just my assumption, though. The question of the eightfold way, though, that's what I'm curious about, because it was Lee group 8. Okay. Particle physics, correct? Right. So, representation theory. That's gonna be so mathematical, isn't it? Lie groups. I'm gonna need the Reblux for this. Is a group. Oh, is that normal mathematical group? Oh, that's group theory. There's also a differentiable manifold, such as the group multiplication taking invisible above the Okay, I need Reblux. Hold on, I'm gonna go to the Reblux's math thing. I'm gonna give him the scientist rank, and I'm gonna go to the Reblux help, and then a crying cat gif. Or gif, whatever you call it. That's how I deal with problems. I just ping mathematicians. In contractions and overlapping particles have been observed radiation. Okay, the question of whether quarks really exist or are instead mathematical concept was not the central importance. That's such a actually great example of. Oh, it's such an amazing. I might also make a video about this too. I really want to make a lot of like shorter videos just about certain fun facts in science, and this would be a prime candidate of how physics works. Just the fact that we don't care exactly if quarks exist, simply because there is no way for us to check if quarks exist. There's no definitive test. Instead, we just check if the theory works. Absolutely love it. We need to want a latter point of view. The important thing is the theory. And the previous array of elementary particles are understandable. A Lie group symmetry is a small set of non-language states quarks. Even better, the theory had predicted new particle states were found in later experiments. That's accurate. They put writing. Even better, the theory okay. The theory worked. Haven't they put rights in some Greek quark? What do you mean, lawmaker? I don't quite understand. A theory of physicists from Thermal Linear Accelerator Center, SLAC, machine technology conducts an experiment which hydrogen electrons were scattered from a proton in a target compound of hydrogen. But they observed a specific number of scatters for which the electron bound of the proton at a sharp angle. Was much larger than would have been experienced if the proton was a uniform blob of charge, 1 fermi-meters across. The size of the proton had been measured on some accounts. Okay, there's an idea. Of the experiments were rather surprising. It would be like throwing a ball bearing into a vat of tapioca pudding and having it bounce back at you. I'm sorry, what is that analogy? The results of these experiments, having a ball bearing about tapioca pudding, having it bounce back at you. Are physicists okay? I don't. Possible instead of being uniform to this blob, the pudding were a suspension of small hard objects. Every once in a while, when you happen to hit one of these small objects, just right, the ball will take a hard bounce, come flying at you. Okay. Why is your mind breaking? I'm just alright, I'm fine. Hi there, Oreo, welcome. This cycling experiment, the electrons counted of the charged proton electromagnetic through the exchange of virtual photon. Yeah. Colourable relation. If the momentum of virtual photon is large, then its wavelength is small. Accordingly, it will scatter over a small region somewhere amid the proton's volume of electric charge. Experiment, the wavelength of the photon for the highest energy scatters was about 10 to 16 meters, or about 1/10 of the proton radius. If the proton is a uniform of charge, then these electrons will scatter over another small fire. And this one won't have much of a mass. That suggested that the proton was mostly empty space, inside of which were tiny subparticles whose combined properties produce the bulk properties of a proton. The proton, it seems, is sort of subnuclear atom. That's a wild thing to say, subnuclear atom. But hey, I dig it. The quarks are going in a way, and further scattering experiments conducted from the point of view confirmed that they had precisely the properties by that model. This demonstration of the physical existence of quarks. Accelerated energies have increased substantially, allowing us to probe atomic nuclei. Alright, makes sense so far. So that's the... Okay, so that's the oh, leptons! We're finished with quarks, okay, that's cool history, I suppose. Which means that for quarks we'll probably need groups, my goodness. Hold on, I'm texting my experts on the matter. What are we reading? Rereading about elementary particles. Hypothesize a smaller set of even more fundamental particles, preons, which these 12 particles are constructed, much as don't-think array particles that so dismayed are economically constructed from the of 3 quarks, the eighth way. No experimental evidence exists for such subnuclear particles, but again, there's no reason to expect them to be as large as 10 to the -5 meters. Okay, so we got the quark so far, for which we have the up, the down, and the strange, funny enough. Which means charm would be different. Bottom and top, I don't quite get what these are either, but okay, it's fine. It's fine. We got this so far. Also, let me take this and let's add it as our source right here. There we go. Simply because, you know. Simply because. Quarks are not the only class of fundamental organisms, but we now understand that quarks make up the nuclei of atoms, but we've known for even longer that atoms are not composed of nuclei alone. We also need electrons. Electrons are the most well-known member of the second class of particles, known as leptons. Yes, they are. Light. Not heavy. Oh, leptons come there. For a second, I thought electrons were named after not heavy, and I was about to have my mind blown. As we discussed it, it's the strong nuclear interaction that binds protons and neutrons, or quarks, together in the nuclei. Electrons are not bound into nuclei; they simply carry the charge associated with the strong interaction. They simply don't carry the charge to the strong interaction. Okay, so they don't have any strong interaction charge. In fact, this is the defining characteristic of leptons. Leptons do not carry the strong force or color charge. Lovely. That's lovely. I love it. It makes sense, it's simple, it's neat. As a result, they don't interact with other matter as readily as strong as objects continuing from quarks. Makes sense. We have quarks interact with strong interaction. Leptons, they don't. Oh boy, and bosons carry it. Wow, it's almost as if it all makes sense. Discovered observe a second type of particle did not participate in the strong interaction. This particle was similar in character to the electron, but with a much greater mass. While the electron mass energy is about 15 mega electron volts, making it light relative to the proton's mass energy. Only 1 billion electron volts, the new particle dubbed the muon was about 100 mega electron volts. So this lepton is not so light. Its lack of strong force charge is what places it in a class with the electron. Alright. The lepton with the electron-like properties, the tau lepton, has mass energy of about 17. That's a big mass, less than 2 billion electron volts. Light indeed. Yeah. Yes, that's 3,000 more than an electron? I was wondering, probably the leptons does not end here. We can step back. Oh, is it going to be an even more massive one? Dating back to rather bold hypothesis regarding radioactive decay of atomic nuclear proof, the process of nuclear beta decay changes the nucleus of one type of atom into nucleus of another. Yeah. In conjunction with the release of electron or positron, in fact, the inability of physicists of that day to describe beta decay in terms of three known forces of nature, gravitational, electromagnetic, nuclear. Oh, that was way before weak and strong were discovered. Prompted them to introduce a fourth force, the weak nuclear force. Where gets that name from? That's actually kind of neat. The only purpose of which at that time was to permit beta decay. Some careful experiments in the 1920s shown that energy was apparently not conserved in beta decay. That seems odd. The energy of the decay products, including the mass energy of the new nucleus produced electron and positron, measured to be less than that of the mass energy original nucleus. Even though the period of weak force behind the process was new and poorly understood, Pauli believed that it could not violate the sacred principle of energy conservation, so he hypothesized that there was a third object taking part in beta decay. To have escaped the detection of all beta decay experiments, this object would have to interact very reluctantly with matter. Oh, is it a neutrino? It would have to be able to pass straight through the detectors of these experimental leaving trace. It's gonna be a neutrino, yeah. Object would have properties different from the previous matter, so he probably felt compelled to hypothesize the existence of a wholly new and different type of particle. This new particle would have to be a lepton with no strong force charge, for otherwise it would interact readily with the matter and detectors. Yeah, right. In addition, this particle could have no electric charge, for which electromagnetic interactions would be enough to have exposed this particle in experiments. What does it interact with then, actually? No color charge, no electric charge. Must interact with something. Otherwise we wouldn't know it exists. Neutrino. I don't know much about neutrinos. Italian-American physicist for which he made necessary use of this particle in the first rigorous theory of the weak interaction. Receiving the 1983 Nobel, but for more or less unrelated work in nuclear physics. Do you mean... Okay, this guy just invented the weak interaction as a hobby. Okay, got it. This ghost-like particle neutrino, which in Italian is saying little neutral one. An electrically neutral, uncharged lepton. So nothing, basically, from what I got so far. An uncharged lepton sounds like nothing. Only in the weak and gravitational forces. Oh my goodness. Is it really just the weak? Oh. The latter of which is extremely weak, even compared with a weak force. The bashful neutrino truly despises making its presence felt. Beam of neutrinos can travel through an entire breadth of the Earth with little attrition. In fact, trillions of neutrinos from the nuclear reactions that fuel the sun pass through your body every second. Very few of which, thankfully, pause to introduce themselves. Ingenuity eventually was referred to the Hemi-neutrino. 1958. Fred Raines the 1995 Nobel Prize in Physics, and Clyde Rowan of the Los Alamos laboratory developed a technique that was able to observe the interactions of neutrinos coming from the core of powerful nuclear reactor. These days, a surprising amount of physics is done with neutrino beams, including, among other things, the study of the properties of the quarks. In fact, I owe my 1988 release from the Institute of Graduate Studies such an experiment. I like it. Hi there, Hungry. It was the Horseman video maker. It was awesome. Thank you. I'm really glad you liked it. Hi there, Mehdi. Welcome. Not much, just light researching. So it only interacts with weak force. That's mad. So right here we are definitely going to go with no, leptons have to be bosons? Oh yeah, bosons, because of the freaking gluon. No, we're gonna do gluons with... no, we're going right here. We'll do up and down. Then we're gonna do strong interaction and gluons. Then we're going to have electromagnetism and photons. Then right here we're gonna have electrons. What else? Quark, no, elementary particles. What we're looking for, of course. There we go. Right here. Electron, then muon, then tau, electron, muon, tau, and then we have apparently 3 neutrinos. All 3 of them. Bosons part 2, no, right here we will have the, actually no, right here we're gonna have weak interaction and WZ bosons, and then no need for connection fundamental, we're still gonna be Higgs with, yes, that's actually shaping up to be quite a nice video. I do like it. This is really advanced physics, I can't stress that enough. Understand none of this, neither do I. Well, maybe a bit. This book helped a lot, I'll be honest. Then back into animation because the section with the matter. Okay, solution with muon. Oh, so we basically have the neutrinos that just turn into electron, muon, tau. There were 2 distinct types of neutrinos. I beg to differ. This history is kind of interesting, actually. What's about top, bottom, and charm, though? Oh, that's not what I meant. Why do we need to just, like... Why can I not turn this off? There we go. It's from elementary particles. Can I? Okay, I can turn this. Alright, top, bottom, charm. Leptons are simple, kind of. The muon and tau will still need some. And then bosons, photon, gluon, K, Higgs, kind of. I'm feeling much better now, I'll be honest. This may not seem like a lot of research, but it really helped me put things in place. Can decay into charm quarks. Bosons can decay into charm quarks? That's wild. That's really wild. I'll be honest, it may not seem like it, but we did a shit ton of work. Pardon my foul language, but truly, this book is outstanding. Where is it? Which one? This one. This book is outstanding. I'm gonna read more of it off stream. I am feeling really tired. Anyway, I'm gonna go now. This might have been a bit of a short live stream. As I mentioned, unfortunately this is the only time I could stream today. So I'm gonna go work on more videos. Not LibraText. Yeah, because LibraText doesn't have a book on the topic. We're reaching like topics in which we can't use LibraText because they don't have it. They don't have anything about the quarks in depth, unfortunately. There are only 2 books about nuclear physics, nuclear particle, which sucks. Anyway, I suppose for now I'll have some rest. Oh no, I'm gonna go back to work on the video. I'm just gonna go work on the video which I don't want to share on stream because it's a secret video. Not a secret video, only a video which I don't work on the stream. Anyway, for now, I suppose that'll be it. Thank you everyone so much for watching and have a great day. Bye.